Welcome to this video on callbacks and higher order functions. These are core principles of the functional programming paradigm in JavaScript. These functions like map, filter, reduce are used every day in professional development environments. And what we're going to do in this talk is we're going to go deep in understanding how to build those functions out from scratch, in order that we develop an intuition of how they work such that we can write them better, debug them better, and deploy them better in our own professional development careers. I recommend you take a look at our first video on the principles of JavaScript, the execution context, the memory, the global variable environment, the call stack, in order to be sure that you have those foundations down, because we're going to be making use of that understanding in this video. But then come join us here and we'll get started on callbacks and higher order functions. So when you write complicated code, complex, large scale code, you're writing thousands of lines, tens of thousands of lines of code, and you've got maybe hundreds of developers working on it, you can't just lay it out, do this, then do this, then do this, then do this. You need some way of structuring that code in a way that is a couple of things. One, really easy for other developers to reason about. So a structure that's just typical, that people just know about. Two, that allows us to add functionality or features to it without any point making it necessarily fundamentally untenable to add more features. Something that's very natural as you build complicated code bases is that adding features breaks previous things. How can you make sure that doesn't happen? And finally, a paradigm, a way of structuring our code that is hopefully fairly efficient, doesn't require too much unnecessary processing power or too much unnecessary memory space. And for years, and we're going to see it later on, the most popular paradigm has been this object-oriented paradigm, where we think about structuring our code around fundamentally objects. In the last few years, and particularly in JavaScript, an emerging popular paradigm, functional programming, has become ever more at the heart of the language. It has two core features that we're interested in. One, pure functions, no side effects. What does this mean? This means that when I run my multiply by 2 function here, its only consequence outside of its little protected window here, its only consequence it has would be by returning a value that would then lead this portion here to evaluate to that returned value 8, and then that 8 to be stored in output. Only consequence it has. At no point would I, for example, inside of the call to multiply by 2, for example, write num++. What that would do is I'd look for num in local, not find it. I would look one layer out, find it, and mutate my global state, change my global memory values. This is risky. This makes it harder for me to test and analyze my function's behavior. If I know its only consequence outside of itself will be whatever gets returned, I can always just look at exactly what this little portion of code evaluates to, and know that I'm not having any other random effects on my code base. You think once you have thousands of variables, thousands of functions, it gets supremely complex if your functions are having side effects. Don't let it happen. That is core principle number 1 of functional programming. Core principle number 2 is these higher order functions. These higher order functions. Higher order functions are something that still make up a huge part of the Codesmith technical interview. Rightly or wrongly, the reason being is not necessarily that they are more significant in the design of the language than other areas. It's more that once you have an underlying mental model of how they're working, we can combine them in fascinating new ways, and then it's up to you in the interview. You can't predict what particular complex combination of higher order functions we will present to you, and that allows us to test the thing we care about most in candidates, or right up there in the top 2 or 3 categories you care about most, which is how do you handle hitting a block in your understanding? When you encounter a block, do you have the tenacity and capacity to navigate through it, even when it doesn't require new information, but as it's combined in new ways, it's a perfect way of testing how you handle hitting a block. But not only that, higher order functions are a highly valuable tool in day-to-day engineering. When you're in a professional environment, they are a highly valuable tool. They're very readable. You'll see functions with names like filter or map, because map is such an intuitive word. I understand where it comes from. Mapping data from one thing to another, okay, through some sort of change of some functionality changing the data in some way. Or reduce, which means reducing a whole bunch of data down to some summary, some single summary value representing that data. These are very intuitive sounding functions, very readable sounding functions. Almost borderline what's called declarative style. I tell you exactly what I want to do. I want to reduce this data using this method for reducing it. It's very explicit. I'm saying exactly what I want to happen. Not necessarily how I want it to happen, but exactly what I want to happen. It's a very popular way of writing functions. So high order functions, and that is going to be the rest of our callbacks and high order functions session. But to begin it, we're going to begin with, I hate metaphors, but we're going to begin with, no, I'm borderline, I'm very impartial, agnostic, no, ambivalent on metaphors. But here is one that we are going to examine. A function that is going to seem so useless that we're going to realize why we have functions at all, and then why we might have these grand higher order functions, so profound higher order, of a greater order than regular functions. We're going to see why we have them. We're going to see why we have them very soon. But first, we're going to create a function, 10 squared. It's going to feel incredibly useful. I'm certain of it. Lewis, talk me through the syntax, for once the wording, not even declare, talk me through the exact wording of this function, 10 squared.
We're going to define a function called 10 squared.
Okay.
It's no parameter.
Perfect, I'm just going to write this up.
It's going to return 10 times 10.
Okay, function 10 squared. No parameters, no inputs, exactly. In the body of the function, it will return 10 by 10. Okay, Lewis, is this a useful function?
Not at all.
It's a profoundly useless function. At least he owned it. It's a profoundly useless function. I call it, and it returns 100. It literally, there is no variability in what it can do. I can't reuse it in some other way. I can't call it and return 80 or 81, probably a better example. I can't reuse it in any other way. It just evaluates 100, so why not just give the number 100? Well, if you like this function, you'll love my next function. See? Tell me how to create a function 9 squared. How do I create a function 9 squared?
Declare a function called 9 squared, and then return 9 times 9.
Okay, very good, see? Excellent. Skylar, create me a function 105 squared. This is more hard, this is more challenging.
So you declare a variable, you pass it an arrow function.
No, okay, this is not. Skylar, give me a simple function, 105 squared.
Declare a function 105 squared, no parameters, in the body you return now.
105 by 105. Okay. These are not useful functions. These are not useful functions, right? A function 9 squared returns 81, 8 squared, 64, 105 squared. Who knows? We have a problem. Our code is getting repetitive. We're building brand new functions for every single number, every single piece of data. But every one of these functions has something in common. What can we do? Just the multiply me by myself bit. Like I'm multiplying some number by myself, and every single function has that in common. And yet I'm building an entire new function for each number, 9 squared, 8 squared, 100 squared. Is there something we could do differently here? Lewis?
You can add a second parameter that takes...
A second parameter?
Yes.
There's no parameters. Just any parameter?
Well, any parameter.
Yeah, you can add any parameter.
You could generalize it.
You could generalize the function by, as Lewis says, adding a parameter. We could generalize our function and create something square num. and then leave a blank num for later when we call square num, fill that blank in with an actual value, 10, 9, 8, 105, whatever. We can say square num is our general definition of how this functionality will work, where it's taking some input and multiplying it by itself, and then don't determine the specific number we're applying that functionality to until we call, until we invoke, until we run that functionality, and leave it generic, leave it general when we define it. So we can reuse it as many times as possible. For 10, to make it live, 10 squared. 9, to make it live, 9 squared. 8, make it live, 8 squared. And this principle of making our functions reusable so that I can take the functionality, multiply me by myself, and reuse it again and again for different numbers, for different data, that principle is going to turn out to be the essence, analogously, of why we have our higher order functions. It may turn out there's not just some data we don't want to determine until we run the function, some number, but actually there may even be some functionality we don't want to determine, we don't want to be specific on until we end up running the function.